Reading Guide. Key Concepts. Essential Questions. How are amplitude and intensity related to energy? What is the relationship among frequency, pitch, and wavelength? How can you recognize sounds from different sources? In what ways are musical sounds produced? Vocabulary: amplitude, intensity, wavelength, frequency, pitch, Doppler effect, interference, resonance. Energy of sound waves. Shh. How do you change your voice from a yell to a whisper? The energy a sound wave carries depends on the amount of energy that caused the original vibration. To speak softly, just use less energy. Amplitude. How do the sound waves produced when you yell and when you whisper differ? The more energy you put into your voice, the farther the air particles move as they vibrate back and forth. For a longitudinal wave, amplitude is the maximum distance the particles in a medium move from their rest positions as the wave passes through the medium. As the energy in a sound wave increases, its amplitude increases. Sound waves with small and large amplitudes are shown in Figure 8. Key concept check. How is the amplitude of sound related to energy? Amplitude, intensity, and loudness. Imagine blowing into a trumpet, like the one in Figure 9. Sound waves leave the horn with a certain amount of energy and, therefore, a certain amplitude. Recall that amplitude is the distance the particles of air vibrate back and forth. Loudness is how you perceive the energy of a sound wave. So, a wave with a greater amplitude will produce a louder sound. Why do sounds get quieter as you get farther from the source? Think of what happens as a sound wave travels away from the horn. As the particles of air in front of the horn vibrate back and forth, they collide with and transfer energy to surrounding particles of air. As the energy spreads out among more and more particles, the intensity of the wave decreases. Intensity is the amount of sound energy that passes through a square meter of space in 1 second. Key concept check. How is the intensity of sound related to energy? As a sound wave travels farther from the horn, there is a larger area of particles sharing the same amount of energy that left the horn. Therefore, the farther you are from the horn, the less energy passing through 1 square meter. This results in less intensity of the wave. As intensity decreases, amplitude decreases. Therefore, loudness decreases. The decibel scale. The unit decibel, dB, describes the intensity and, in turn, the loudness of sound. Decibel levels of common sounds are shown in Figure 10. Each increase of 10 decibels indicates the sound is about twice as loud and has about 10 times the energy. For example, the decibel level of city traffic is about 85 decibels, and the level of a rock concert is about 105 decibels. This means a concert, which is 20 decibels higher, has about 10 times 10, or 100 times, more energy than traffic. Recall that a loud sound can make the eardrum vibrate so hard that it tears. As sounds get louder, the amount of time you can listen without hearing loss gets shorter. Describing sound waves. Sounds depend on many properties of the sound waves that enter your ear. Loudness or softness depends on the amplitude of the wave. You also might describe sound according to how frequently the waves occur or how long the waves are. Wavelength. One property of a sound wave is its wavelength. The distance between a point on one wave and the nearest point just like it is called wavelength. For example, you could measure a wavelength as the distance between the midpoint of one compression, or rarefaction, and the midpoint of the next compression, or rarefaction, as shown in Figure 11. Frequency and pitch. Suppose you could count sound waves produced by playing middle C on a piano. You would find that 262 wavelengths pass you each second. The frequency of sound is the number of wavelengths that pass by a point each second. Notice in Figure 11 that as the wavelength of a sound wave decreases, its frequency increases. The frequency of one vibration, or wavelength, per second is called a hertz, Hz. The frequency of middle C on a piano is 262 hertz. The perception of how high or low a sound seems is pitch. A higher frequency produces a higher pitch. For example, an adult male voice might range from 85 hertz to 155 hertz. An adult female voice might range from about 165 hertz to 255 hertz. The human ear can detect sounds with frequencies between about 20 hertz and 20,000 hertz. Frequencies above this range are called ultrasound. The range of sounds heard by various animals is shown in Figure 12. Key concept check. What is the relationship among frequency, pitch, and wavelength? The Doppler effect. You might have heard the high pitch of a train whistle as the train approaches. As the train passes, the pitch drops. Sound frequency depends on the motions of the source and the listener. Compare the wave frequencies in front of and behind the moving train in Figure 13. The frequency increases if the distance between the listener and the source is decreasing. The frequency decreases if the distance between the listener and the source increases. The change of pitch when a sound source is moving in relation to an observer is the Doppler effect. Sound interference. If you walk through a room with stereo speakers at each end, the sound might seem louder in some places and softer in others. The waves from each speaker interact with one another. Interference occurs when waves that overlap combine, forming a new wave. Figure 14 shows why this happens. When compressions meet, they join to form a wave with higher intensity and greater amplitude. This is called constructive interference. However, when a compression meets a rarefaction, the intensity and amplitude decrease. This is destructive interference. Beats. Have you ever been to a concert where the musicians start by all playing the same note? Why do they do that? If the pitches of the notes are slightly different, the sounds will interfere. The audience might hear the notes get louder and softer several times a second. The repeating increases and decreases in amplitude are beats. Look back at Figure 14. The difference in frequencies determines how often beats occur. If one musician plays a note with a pitch of 392 hertz and another plays a note with a pitch of 395 hertz, the difference is 3 hertz. Beats will occur 3 times each second. Musicians can avoid beats by playing notes at the correct pitch on their instruments. Fundamental and overtones. When a musician plucks a guitar string, the string vibrates with a certain sound. If the musician plucks it again in the exact same way, the sound will be the same. All objects tend to vibrate with a certain frequency that depends on the object's properties. The lowest frequency at which a material naturally vibrates is called its fundamental. Higher frequencies at which the material vibrates are called overtones. Objects vibrate with both a fundamental and overtones, as shown in Figure 15. The interference of these waves produces the sound you hear. Reading check. What is the difference between a fundamental and overtones? Music. Have you ever been listening to your favorite music and someone tells you, "Turn off that noise"? How are music and noise different? Unlike noise, music is sound with a pleasing pattern. Sound quality. The unique sound of a musical instrument is a mix of its fundamental and overtones. These waves interact to form a distinct sound, or timbre. Suppose, for example, a clarinet player and a piano player both play the same note. The fundamental of both instruments is the same. The number and intensity of the overtones, however, differs. Overtones produce the complex sound waves that let you distinguish the unique sound quality of each instrument. Key concept check. How can you recognize sounds from different sources? Resonance. If you hold a guitar string by its ends and have a friend pluck the string, the sound is almost too low to hear. Instruments use resonance to amplify sound. Resonance is an increase in amplitude that occurs when an object vibrating at its natural frequency absorbs energy from a nearby object vibrating at the same frequency. The vibrating string causes the back of the guitar and the air inside to vibrate by resonance. The sound is then much louder. Types of musical instruments. As shown in Figure 16, different types of instruments control the pitch and the loudness of sound in different ways. String instruments. Musical instruments that have strings, such as a guitar, a violin, a harp, and a piano, produce sound when the string vibrates. A player plucks the strings of a guitar or a harp. The motion of a bow vibrates the strings of a violin. Pressing a piano key causes a felt-covered hammer to strike a particular string inside the piano. When the string inside the piano vibrates, you hear a tone. The pitch a string makes depends on its length and its thickness. Pitch also depends on how tightly the string is stretched and the material it is made from. You can hear sounds a stringed instrument makes because of resonance between the string and the instrument's hollow body. Plucking or pressing the strings harder increases the volume. Wind instruments. The vibrating medium in wind instruments, such as a saxophone or a trumpet, is air. Either your lips or a thin piece of wood, called a reed, vibrates. An air column then vibrates by resonance. The length of the air column determines pitch. Blowing harder increases the volume. Percussion instruments. You make sound with a percussion instrument by striking it. Examples include a drum, cymbals, and a bell. The pitch depends on the instrument's size, its thickness, and the material from which it is made. Resonance can make the sound of a percussion instrument louder. Voice. The source of sound in your voice is vocal cords. Muscles in your throat allow you to increase the pitch of your voice by pulling the cords tighter. Other parts of your mouth and throat also affect the sounds your voice makes. You can make your voice louder by pushing out the air with a greater force. Key concept check. In what ways are musical sounds produced?